This is Professor Corey. In this lecture, we'll begin Chapter 6, which is Acid-Base Chemistry. Our last lecture completed chemical equilibrium, and more specifically, using Le Chatelier principle to explore shifts in equilibrium concentrations when a change is made to a system that's in equilibrium. These are some methods of defining an acid and a base, and we're going to primarily focus on the Bronsted-Lowry method, where a substance is labeled an acid if it donates a proton in a chemical reaction. By this definition, a base is a proton acceptor. You will see the proton represented as a hydrogen ion, and if you consider the subatomic particles of a hydrogen atom, we have one proton and one electron, and you'll realize that if the hydrogen atom loses the electron and becomes an ion, the only particle remaining is the proton. The Arrhenius definition of an acid is a substance that increases the hydrogen ion concentration when dissolved in water, with the base increasing the hydroxide ion. This is a good definition, but it's limited, as you'll see in upcoming lectures. The Lewis definition involves tracking electron pairs during chemical reactions. If we carefully examine the first reaction, you can see that the HNO3 is donating a hydrogen ion and becoming the nitrate ion, while water is accepting the proton to become H3O+. This is referred to as the hydronium ion, and we'll discuss how this may exist in more detail later. The second reaction shows how water can act as an acid. In this example, the ammonia is accepting the proton to become the ammonium ion. A strong acid, by definition, will completely dissociate into ions in water. This is not considered an equilibrium reaction, as it only proceeds in the forward direction, as noted by the single arrow. There are 6 strong acids, and you'll be required to know these. A weak acid will not completely dissociate in water. Strong bases act similar in that they completely dissociate into ions in water. A simple definition for a strong base is that it is a group 1 or 2 metal hydroxide, which means there's a metal from group 1 or 2 in the periodic table combined with an OH group. This is a chart from your textbook that lists some of the common acids and bases. You will need to memorize the 6 strong acids and the weak base ammonia. Monoprotic acids have one donatable proton or hydrogen ion. Some acids have more than one. You may see the term polyprotic, which refers to more than one, or a more specific term like diprotic, referring to 2 donatable protons, or triprotic, which would be 3. An important note is that not all hydrogens are donatable, and just having some experience will help you see this. One rule that might be helpful at this point is that hydrogens that are attached to a carbon atom are not donatable. So the structure on the right of the image has 6 hydrogens, but only one of those is donatable. So this is a monoprotic acid. A conjugate acid-base pair exists for every acid-base reaction. You will be responsible for being able to identify these pairs. This is a chart from your textbook that shows the conjugate acid-base pairs, and realize that the difference in the conjugate pair is 1 hydrogen. So HCl and Cl- are conjugate pairs, while H2O and H3O+ are conjugate pairs. We can calculate an equilibrium constant for acid-base reactions, and this is sometimes called an ionization constant. If the value is large, it means the reaction is product favored. Strong acids, therefore, will have large ionization constants because they completely ionize in water. Notice in the expression that water is not included because the state, it's the liquid state, and that's not included in our expression. We saw earlier that water can act as an acid by donating a proton. Well, water can also accept a proton to form the hydronium ion. Pure water will auto-ionize, forming the hydronium and hydroxide ions. This equilibrium is very strongly reactant-favored, however, as seen by the equilibrium constant for water, noted as Kw, with a value of 1.00 times 10 to the negative 14. Since the liquid state is left out of the expression, this value is the multiple of the ion concentrations, and we can say that each ion has a concentration of 1 times 10 to the negative 7. pH is a measurement of the amount of hydronium ion in solution. In a neutral solution, the hydronium ion is equal in concentration to the hydroxide ion, and both will have a concentration of 1 times 10 to the negative 7. Acidic solutions have more hydronium ion than hydroxide, and basic solutions have more hydroxide ion than hydronium. pH is determined by taking the negative log of the hydronium ion concentration. Likewise, we could calculate a pOH by taking the negative log of the hydroxide ion concentration. The sum of pH and pOH is equal to pKw, which is 14. Try this using your calculator. Kw is 1 times 10 to the negative 14. Take the negative log of this value, and you should get 14. Likewise, we can determine the hydronium ion concentration if we have the pH. This is calculated using the anti-log, or second function log, log, on your calculator. Assume you have a pH of 7 and calculate the hydronium ion concentration. You should get 1 times 10 to the negative 7 on your calculator. Kw is the product of the hydronium ion concentration and the hydroxide ion concentration. So we can rearrange this relationship to solve for the other if one is known. Remember, Kw is known. That value is 1 times 10 to the negative 14. This image is really a nice summary of the pH scale, although it actually extends beyond 0 and 14. But make sure that you can calculate pH given a hydronium ion concentration, as well as calculate the hydronium ion concentration given the pH. You should also be able to obtain the pOH and the hydroxide ion concentrations if given a pH. This slide outlines the relationships between pH, pOH, and concentrations of hydronium and hydroxide. It will be very beneficial to be able to perform these calculations quickly. A good exercise would be to start with a pH. You can just make up any pH and calculate hydronium ion concentration, then hydroxide ion concentration, pOH, and back to pH. Your starting and ending pH should be the same if the calculations are performed correctly. Much information was covered in this lecture. We started with acid-base definitions and quickly moved into calculations involving pH. In our next lecture, we're going to use ice tables to calculate equilibrium concentrations for acid-base reactions. Stay tuned, and thanks for watching the Professor's DuBois channel.